This is Dr. Shankaraiah from Department of Physics. Today, the topic of the presentation is surface to volume ratio and quantum confinement. So, this is module 5, which is nanotechnology. So, why these two properties, surface to volume ratio and quantum confinement, are important in nanotechnology? So, the phenomena due to which properties of nanoparticles are different. Why these two properties change or affect the properties of nanoparticles. Okay, so the two properties, the two phenomena due to which the properties of nanoparticles are different, are the two phenomena are surface to volume ratio and quantum confinement. Because of these two phenomena only, the properties of these particles are different. Okay, so what is this surface to volume ratio? Surface to volume ratio. So nanoparticles or nanomaterials have relatively large surface area when compared to the same volume or mass of the material produced in larger form. Okay. So nanoparticles or nanomaterials have relatively large surface area. If you take this nanomaterial and look at the surface area of this nanomaterial and look at the same volume of the material which is in bulk, then we will find that the surface area of the nano-sized materials is more compared to the material which is in the bulk form. Okay. So, why does this surface to volume ratio increases for nanomaterials? That we will see. Okay. So, to understand why surface to volume ratio increases for nanomaterials, we are taking two examples here. First, consider a sphere of radius r. Okay, if you take a sphere of radius r, for a sphere the surface area is 4 pi square. 4 pi square r square. 4 pi r square is the surface area. Okay, surface area is 4 pi r square, and volume of cube is 4 by 3 pi r cube. So this is for a cube. Sorry, for a sphere. So we are taking the first example as a sphere. Okay, and we are trying to look at the surface area to volume ratio of a sphere. For a sphere, the surface area is 4 pi r square, and for volume of the sphere is 4 by 3 pi r. Now, so with this we can calculate surface area to volume ratio, and surface area to volume ratio is, so first surface area is 4 pi r square, and its volume of a sphere is 4 by 3 pi r cube, right? So 4 pi r square divided by 4 by 3 pi r cube. So here square is there, here cube is, so r square will go away, we will have r, and 4 will cancel, 5 will cancel. So what we will get is 3 by r, because 3 will go to numerator. So surface to volume ratio of a sphere is 3 by r. That is what we find. Okay. So now for the second example, to understand the surface to volume ratio, I am taking the second example as a cube. I am taking cube. You can see here clearly cube, right? So cube. Okay. So for a cube, the surface to volume, the surface area of a cube is 6r square. Okay. So cube. Next example, to understand surface to volume ratio, I am taking as cube. Okay. So this is the first example is sphere, and second example is cube. For a cube, what is surface area? Surface area for a cube is 6a square. Why is it 6a square? If I take length of each side, length of any one of the side is a, it's a cube. Cube, all sides are equal length. Okay, so a is right. See, each cube has 6 faces, right? And the area of each face is a square. Why? Because each face is a square. Okay, area of a square is a square, right? So area of a square is a square, and 6 such squares, because each face, 6 faces are there, right? So let me write it neatly. So 6 faces for a cube, 6 faces first, and each face is a square. Each face is a square. square. Area of a square. Area of a square is what? Area of a square is a square. If a is length of each side, the area is a square. So area of a square is a square, and for a cube there are six such faces, and each face is a square. So that is why surface area of a cube is 6a square. Okay. Now volume of a cube. Volume of a cube is a cube. We all know that volume of a cube is a cube. So now 6a square is the surface area and volume is a cube. Okay. So 6a square by a cube. A square will go away. So you just left out with a here. So 6 by a is the surface to volume ratio for a cube. So for a sphere, the surface to volume ratio is 3 by r, where r is the radius. For a sphere, r is the radius. R is the radius of a sphere. And for a cube, surface to volume ratio is 6 by a, where a is side of or length of each side of a cube. Now, suppose to understand this, why surface area to volume ratio increases as we decrease the size, as we reduce the size of a material, we are going to find that the surface to volume ratio increases, and at a certain size, we are going to find at a certain side in the scale, in the nano scale, we will find the properties of such a material will change. Okay. Now, so for example, I am starting with this cube. This cube, each length. Okay. Now, to understand that surface to volume ratio, I have considered as a, but here I am taking the length of each side is 1 meter. Okay. So I am taking this to understand why surface to volume ratio increases as I reduce or decrease the size of the material. Okay. Now I have taken this cube. I have a material, and the material has all cubic unit cells. Okay. So this, I have this cubic unit cell, and length of each side is 1 meter. So the surface area is 6 into 1 meter square. So that is 6 meters square. Now the surface area of this particular cube is 6 meters square. Now I have cut this cube into four equal parts. Actually, so 8 equal parts. I have cut this cube into 8 equal parts. Okay, I have divided this 1 meter length cube into 8 equal parts. Okay, so now what is the surface area of this? 6 faces into 1 by 2 meter, because the length of each side is 1. But now I have divided each length into 2 parts. Okay. So the area of each part is now 1 by 2 meter square. 1 by 2 into 1 by 2 meter square, that is 1 by 4. And then how many such parts are there? How many such cubes are there? 1, 2, 3, 4, 5, 6, 7. And then there is one more cube beside this, there is 8. So there are 8 such cubes. So when I divide this each side, when I divide this cube, each side I am going to cut into. So 1 meter I have cut into 1 by 2 meters. So here also there is 1 by 2 meters. So here also there will be such. So here also there will be like that. So totally there will be 8 such parts. And then when I cut into 2 equal parts, so the length of this cube will be 1 by 2. Each side 1 by 2. And the length of this one also 1 by 2 each side. So then the surface area of such cube, which is divided into 8 equal parts, will be 12 meters square. So the surface area now increased to 12 meters square when I cut this cube of length 1 meter into 8 equal parts. Now, okay, 6 meters square when I have the length of each side 1 meter. 12 meters square when I have divided this 1 meter into 2 equal parts. So 1 by 2 meter. So totally there are 8 such cubes. Now I am going to further divide this cube. So now I have divided this cube into 27 equal parts. So now instead of 1, the length of each side is now 1 by 3 meter. 1 by 3, 1 by 3, 1 by 3. Okay. So when I divide this cube into 3 equal parts, then there will be 9 into 3, so 27 equal parts. And so now the surface area of such cube, which is divided into 27 parts, 6, each cube is going to have 6 faces. So 6 into 1 by area of each face. Area of each face is 1 by 3 meter square. So that is 1 by 9 meter square, and then 27. Totally we are going to get 18 meters square, right? So this is 9, yeah. So 6 into 1 by 3 whole square, because area square. So 1 by 3 into 1 by 3, 1 by 9 into 27 such parts. So 9 3s are 27. So 3 into 6, 18 meters. So the area now, surface area of this 27 cubes. Now the surface area of this cube is 18 meters square. And then I am going to further divide into smaller and smaller parts. I am going to find the surface area is going to increase. When I divide this cube into small parts, where each length of the cube is 0.1 nanometer. Okay, I divide it into smaller grains, small grains. Each grain, each small cube, the length of each side of such cube is 0.1 millimeters. Then I am going to find the surface area is going to be 2.5 acres. Okay, so we can understand clearly from this example or exercise that the surface to volume ratio increases when we decrease the size of considered unit cell. Here I have considered cubic unit cell. So when I divide this cubic unit cell into smaller and smaller parts, I found out that the surface to volume ratio increases enormously as I divide further and further smaller grains. Okay, so we can clearly see that as we reduce the size of these smaller grains, we find that the surface to volume ratio increases. So that is the reason why the surface to volume ratio is one of the important phenomena because of which the properties of a nanomaterial changes. Now, so as RRA decreases, here we can clearly see R is in the denominator for sphere and A is also in the denominator for cube. So as we reduce the size, A is going to decrease. As we decrease A, or as we decrease, first we take large sphere, R is more. I reduce the size of the sphere to small, R by 2. As I reduce further, R by 4. So as I decrease the size of the sphere or cube, we are going to find that the surface to volume ratio increases. It's clear from the equation of the surface to volume ratio. Okay. So as RRA decreases, surface to volume ratio increases. So the properties of materials will be changing. Okay. So this is one of the most important phenomena due to which the properties of a nanomaterial change, that is surface to volume ratio. The material has high surface area if it is small in size or vice versa. If the size is more, the surface to volume ratio less. If size is small, surface to volume ratio high. Okay. So the surface energy will be more if size is small. As the surface area to volume ratio increases, the material possesses good catalytic properties. Thus, nanoparticles show enhanced stability and broader scope of applications. As we decrease, when we take a bulk material and reduce the size of these material, going to smaller and smaller nanoparticles, then we find that some of the material which is not catalytic, which is in bulk size, then that material can become a catalyst when we decrease or when we fine grain this material. Okay, so when we get these nanoparticles or nanomaterial, then they can exhibit this catalytic behavior and they will be more stable. They will be more stabilized and they will be having broader scope in application. So surface to volume ratio is one of the important properties. In some cases, materials that are inert, which do not exhibit any property, or when we apply some external force or external field, then they are called inert. Okay, in materials that are inert in their larger form are reactive when produced in the nanoscale form. So what we are saying is that some materials which are not catalytic in bulk form, they can become catalyst when we fine grain this material into nanomaterials. Okay, so materials which are not catalyst becoming catalyst when they become nanomaterials or nano-sized materials. Materials which are inert, which do not exhibit any change in the properties when we apply external field, which are called inert materials. So materials which are inert in the larger form, I mean in the bulk form, can become reactive when we produce nanomaterial. When we fine grain the material, take a bulk material and check whether it is inert or reactive. Inert means it do not, when you apply some field or when you add some chemical, it do not show any change in their properties, which are called inert. Now, get nanomaterial from this bulk material by fine graining them, then we can find that the material is going to become or reactive. So it is going to exhibit some properties, change in properties when we apply some external field. Okay, so this affect their strength or electrical properties. So material which are in larger form inert, but they are becoming reactive when we reduce them in the nanoscale form or small scale form. For example, a particle of size 30 nanometers has 5% of its atom on its surface. When you have a particle, nanomaterial, and its nanoparticles of size 30 nanometers, and we can put only 5% of such atoms on the surface. But now 10 nanometer, when we decrease the size of this particle, 20% of atoms and 20% of atoms we can place on the surface of it, and when we reduce the size into 3 nanometers, we can put 50% of its atom. Okay, so to understand this, we can take off a drug. We have a drug and we want to deliver this drug to a particular organ in our body, and we are going to put some percentage of drug on this. We are going to send some percentage of drug into the body. Okay, suppose if you have a smaller and smaller size particles, then we can put more of them. So that is why surface to volume ratio is very small. So when you reduce the size, we can put more and more small nanoparticles on the surface of a drug. So that is all about surface to volume ratio. So we find that as when the surface to volume ratio increases, the materials which are inert can become reactive, and materials which are not catalytic can become catalyst. So surface to volume ratio is one of the important phenomena that changes the properties of a material, especially in nano form. So the second phenomena which is very important in nanotechnology is quantum confinement. Okay. So what is this quantum confinement and how does it affect the properties of a nanomaterial? When atoms are isolated, the energy levels are discrete. Okay, so we know that atom when a particle or when an atom is isolated or trapped in a particular potential well, we find that the energy levels are discrete. So this, to understand why the energy levels are discrete when atoms are isolated, if we recall the particle in one-dimensional box in quantum mechanics. In quantum mechanics, we study the particle trapped in an infinite potential well, right? So this is the infinite potential well. So this is the particle that is trapped in this infinite potential well. The potential is 0 inside the well. That means particle can move freely here and there inside the well. But the potential is infinite at the boundaries. That means the particle cannot escape this potential well. It is trapped. Okay. And the length of this one-dimensional box is E. So we can solve the Schrodinger wave equation for this particle in one-dimensional box, and so for a particle in one-dimensional box, we have solved Schrodinger wave equation. So dou square psi by dou x square plus 2m e minus v by h cut square into psi is equal to 0. So this is time-independent Schrodinger wave equation in one dimension. So we solve this time-independent Schrodinger wave equation, Okay. So time-independent Schrodinger wave equation in one dimension. So when we solve this Schrodinger wave equation for this problem, which is a particle trapped in an infinite potential well, we find out that the wave functions are sin of x is equal to square root 2 by a sin n pi by a into x, and energies En are n square h square by 8m a square. So that means En, for example, n is equal to 1, that is the first energy level, is h square by 8ma square. And n is equal to second energy level, 4h square by 8ma square. N is equal to 3, 9h square by 8ma. N is equal to 4, 16h square by 8ma. That means when a particle is trapped or isolated from the surroundings, then we find that the energies of such a particle will be discretized. There are no continuous energies. Like for a classical particle, you can have any energy 0.1, 0.2 or 0, minus, plus, right? So, but a particle that is isolated or trapped in an infinite potential, we find that the energy levels are discrete. So that we can see clearly here, and these are the wave functions. So these are the wave functions and these are the energy levels. So when a particle is trapped or when an atom is isolated, we find that the energy levels are discrete. Okay. Now, if we take group of atoms, here this atom is isolated and we find that the energies are discrete. Now, when we take very large number of atoms, okay, when we take group of atoms and when we take group of atoms to form a solid, molecular orbital form as shown in figure. Okay, so for a one isolated particular atom, the energy levels are discrete. But now I am taking many such atoms and putting together. When we take many atoms and put together, we find that they can be a solid or a liquid or a gas. But here I am putting together close, so that is why we see there is a formation of solid because atoms are close by. Okay, so when we take large number of atoms closely packed to form a solid, we find that orbitals form. Okay, so for example, to understand why orbitals form, molecular orbitals form, or why there is energy level splitting, here we can see energy bands. Okay, so there for an isolated atom we have discrete energy levels, but when we take more large number of atoms to put together, then we find that there are continuous energy levels. So to understand that, here I am taking small example of hydrogen atom. So this is one hydrogen atom A, and this is hydrogen atom B. So each hydrogen atom has one of the electron, 1s1, right? Each hydrogen atom has only one electron, so that is 1s1. So this is the orbital corresponding to 1s1 or 1 electron. Okay, so this is A hydrogen atom and this is B hydrogen atom. So each electron is in the orbital. Now I took these two hydrogen atoms and I am putting together. Okay, when I put together, there is a overlap between these orbitals. Okay, hydrogen atom A orbital and hydrogen atom B orbitals can overlap when I put these two hydrogen atoms together. When I take two independent hydrogen atoms and put together, I am going to see there is a hydrogen molecule. Two hydrogen atoms, when they are grouped together, we find there is hydrogen molecule H2. When we see hydrogen molecule, we find that these orbitals, hydrogen atom A and hydrogen atom B orbitals will overlap. And the overlap can be in two ways, bonding orbitals and anti-bonding orbitals. So based on this overlap, you can have two different types of orbitals and you will see there is a molecular orbital formation, psi plus and psi minus. When there is molecular orbital formation, we will see there will be energy level splitting. Okay, so this energy level is hydrogen atom A and this is the energy level of hydrogen atom B, because two hydrogen atoms having same energy levels. When we see there is a hydrogen molecule formation, these energy level will split into two more energy levels and there will be four such energy levels. See, to understand this energy level splitting clearly, you can see here, so there are two hydrogen atoms together and then you see there are four such energy levels. Each hydrogen atom has only one energy level, E1 and E2, but now these two energy levels have split into E1 prime and E2 prime because of bonding orbital and anti-bonding orbital. So these two orbitals can overlap in two ways, psi plus and psi minus. So because of this bonding anti-bonding, these two energy levels are going to split into four energy levels as shown here. So suppose if you take three hydrogen atoms, for example, three hydrogen atoms putting together, you see these three energy levels, E2, E1, E2 and E3 will split now into six energy levels, right? Similarly, as you take more and more hydrogen atoms together, you will find there is energy level splitting and you will find there are energy bands. Okay, so this is one energy band and there is another energy band. So you can have a valence band and conduction band. So that is how these bands form. So lower energy level is valence band and higher energy level will be conduction band, for example. Okay, so when you have isolated atom, the energy levels are discrete. Energy is discrete. Now I have group of atoms. When I have group of atoms to form or to make a material, I find there are energy bands. Energy bands where so many energy levels are very closely spaced. Okay, so now, so we know that these nanoscale is the boundary land between macro and micro. So what happens in this now? Nanomaterials represent intermediate stage. So that is what I said. Nanomaterials are between micro and macro. Okay, so our quantum are macro. Okay. So when the dimensions of the box of potential wells in which particle is trapped are confined are of the order of de Broglie wavelength of electron, energy levels of electrons change. Okay, so this effect is called quantum confinement effect. So when we are taking isolated atom, energy levels are discrete. When we have many atoms, energy levels are continuous, right? Now, when the dimensions of the box, we have taken one potential box. When the dimension of the box or the potential well in which particle is trapped is the order of the de Broglie wavelength lambda, then the energy levels of the materials will change. So you have many particles. There are nanoparticles. And each particle is, if the particle trapped in a potential well, the size of this potential well is matching with the de Broglie wavelength that particle, then the energy levels will change, and such a confinement is called as quantum confinement. When the material is sufficiently small in size, typically nanometer, 10 nanometers or less, organization of energy levels into which electrons can climb or fall will change. So energy levels will change. They will be different when you have this quantum confinement effect. What do you mean by quantum confinement exactly? If we are taking this particle, nanoparticle, the size of the nanoparticle is matching. The size of the nanoparticle is matching with its de Broglie wavelength. So size of the nanoparticle is matching with the de Broglie wavelength. When the size of the nanoparticle matches with the de Broglie wavelength, that means that there is quantum confinement. And when you have this quantum confinement, the energy levels will change. They will be neither discrete and they will be neither continuous. There is a different kind of energy level distribution. In small nanocrystals or clusters or grains, the electronic energy levels are not continuous as in bulk, but are discrete. So we are taking nano material which have many nanoparticles. But when we have many such small particles, we expect that these energy levels are continuous. But find, even though there are many such nanoparticles, the energy levels are discrete, which we expect only in bulk materials. Okay, so that is what we find. So because of the confinement of the electronic wave function to the physical dimensions of the particle. Okay, so when the particle size is in the nanoscale, then even though there are many such nanoparticles, we find the energy levels are not continuous, but the energy levels are discrete, which we expect only for isolated atoms. So these can affect the optical, electrical, magnetic behavior of materials, particularly as the structure or particle size approaches the smaller end of the nanoscale. As the particle size approaches this nanoscale, we find many different properties, for example, optical properties, electrical properties, and magnetic properties of materials change. Okay, so examples of such quantum confinement: opaque substances become transparent. Okay, materials, for example, copper. So examples of quantum confinement, where the properties change, right? So some of the opaque substances becomes transparent when they change when we change the size into nano size, right? So inert materials will become catalysts, stable materials become combustible, and solids turn into liquids, and insulators become conductors. So these quantum confinement can change the properties of materials. Okay. So these are some of the references, textbooks and some reference books which are used in this presentation. And to summarize, in this presentation, I have discussed about two important phenomena. Okay, two important phenomena that affect the nanomaterials. Two important phenomena. The two important phenomena are, first one is surface to volume ratio. Surface to volume ratio, and second one is quantum confinement. So we find that as we reduce the size of a bulk material, the surface to volume ratio increases, and hence the properties can change. For example, inert materials can become active materials, non-catalysts become catalysts. Similarly, quantum confinement, when we decrease the size of the particles into nanoscale, then we find that the energy level distribution, which is expected to be continuous, we find the energy levels will be discrete even though there are many such particles. So that is quantum confinement. So because of these two important phenomena, surface to volume ratio and quantum confinement of nanoparticles, nanomaterials, the properties of the materials change and they exhibit different properties. Okay, so yeah, I'm going to stop here. In the next presentation, I will discuss about some other topic in nanotechnology. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.